Welcome to 15-day industrial training program on AI-driven embedded product development lifecycle. So today is day 5. It's about PCB layout and routing techniques. So coming to SSIT, we are certified by SWAYAM Plus, AICTE, and AppG, and ISO certified, and MSME Startup India. These are some of the certifications. So coming to today's table of contents. So today we are going to discuss about component placement strategy for power, analog, and digital circuits. So there are, if you take PCB designing, there are three major segments. One is power related segment, analog signal related, and digital signal related. So there are, we need to take care about component placement for these three aspects. That is the first topic for today's session. And thereafter, trace routing techniques. We are going to discuss about single layer and multi-layer, and followed by PCB design constraints and rules, which are the design rules we need to follow for PCB design, and followed by power and ground plane design for stability, and followed by hands-on. Here we are going for a routing a PCB design using easy EDA. Thereafter, we will discuss how AI will minimize the manual work and improve the design constraints, layout, schematic drawing, and layout development. So this is about today's session. So we are planning today. I am planning both theory and practical simultaneously. So if you are having any doubts, you can stop at that moment. I would like to resolve the doubts at that instant, and Mr. Sai Shankar will join by 8 or 8:10. So at last 10 minutes, he will handle doubts clarification. Yeah. So thing here is, there are already I told, right, there are three major segments. One is power segment, and analog circuits, and digital circuits. First, we will focusing about how should we take care about power segment. So is PCB is visible for you guys? So if you take this particular PCB, so in this particular PCB, there are power circuit and analog circuit and digital circuit. So basically, we need to separate all the circuits in a different placements. So we need to separate power circuit as a separate block, and analog circuit as a separate block, and digital as a separate block. Why should we take care about this separation? So we will see in detail. So coming to power modules in a PCB, typically MOSFETs, voltage regulator, and inductors. These are we can consider as the power related components in a PCB design. So the first thing, we need to place all those components as close as possible to reduce the trace, resistance, and inductance. So let me explain. So if we these power related modules will dissipate too much power, too much temperature, heat, we can say, because every power module, let us assume, let you take voltage regulator. Basically, if the input is 12 volts and there is a 5 volts regulator, so from 12 volts to 5 volts regulation, when the conversion is taking place, the heat will be produced. That heat will create the noise. So in a PCB, we need to place all the power related modules as a separate module, or else we can keep as far as for both analog and digital circuitry. So to reduce the resistance and inductance. And one more thing, we should use wide range of wide width of traces, because, so let me explain this particular concept with the water pipeline. If we take the water pipeline from water reservoir, there is a huge radius of tube we are keeping for water distribution. While it's coming to the villages, it's going for a small tubes. While coming to the home, the radius of the tube will be getting lower. The similar way, these particular power related domain will produce high power. These are the systems which need to take care about all the power requirement of both analog circuit and digital circuit. So we should maintain high width of tracks for to allow the higher current, higher voltages. So that is what the meaning of, we need to maintain wider traces and thicker copper to engage higher currents and to reduce the heating. Like, let me explain. If the tube is in lesser volume, lesser radius, if we are trying to push high volume of the water, then there will be a chance for a blasting of the particular tube. Same thing for power segment. If the track width is lower, if you are able to, if you want to send the higher current through that particular trace, then there will be a chance of damage of that particular track. So we need to maintain a higher track width to allow uh, higher currents. And one more thing, we need to minimize this particular loop area. Loop area means there should be we should not maintain unnecessary spaces on the PCBs in power circuitry, because it will increase the size of the particular PCB. So we should keep all the components as close as possible, so that all these electronic power rated components will produce higher EMFs. So if you are maintaining wider space between these particular components, that EMF will affect the both analog and digital signals. So there should be a separation. We should maintain separation between analog circuitry or analog digital from power segments. So MOSFETs, voltage regulators, these are the power related components. We should maintain separation from analog and digital circuitry, and we should reduce the minimization of that track, which should be very high. So these are the sum of things we need to follow. And one more thing, we need to place decoupling capacitors. The purpose of decoupling capacitor is to reduce the noise filtration and glitches filtration. So for this particular purpose, we need to place this particular decoupling capacitors as close as possible for the heat generation elements. Basically, all the power related elements will deal with the heat sinks. So we will discuss in the upcoming slides. So what are the things we need to take care? What are the things we need to avoid while designing of this particular PCB? So coming to analog circuitry components, basically we need to keep all analog signals path as short as possible, because analog signals are continuous in nature. Even if the length of the track, it's not about, in coming to the power related components, we are talking about width of the track. The width of the track is as much as possible. Coming to the analog signals, the length of the track is minimal, because while the length of the track is increasing, then there will be a chance for a signal degradation. So we should maintain tracks as minimum as possible. And one more thing, we should maintain isolation between high speed digital signals. There should be an isolation between digital signals and analog signals, like digital circuitry and analog circuitry, because the digital circuitry switching is quicker, because the digital circuitry is zeros and ones. The transaction period is too quicker. So when the digital transaction is too higher, so we can say like a high speed transaction signals. So we should maintain isolation between analog circuitry and digital circuitry to make to avoid crosstalk. So signal may interference with digital signal, and digital signal may interference with analog signal. So we should maintain some isolation between analog and digital circuitry. And one more thing, we should use solid ground panel under analog sections, because these ground panels will reduce the noise. So digital signals doesn't require it is required, but not that much dependent on the solid ground panels. But coming to the analog, we should maintain solid ground panels. So this is about this particular analog circuitry. So track should be as short as possible, and decoupling capacitors should be placed very close to the analog ICs. So this is the line point for any designs. If it is a decoupling capacitors for power circuits and analog circuits, we should place decoupling capacitors as close as possible, because the high frequency, the high ripples will be filtered at the source itself, so that it won't affect other signals. So there will be no chance for crosstalk of the signals. So this is about analog circuitry. And coming to the digital circuitry, this simply like we should maintain separate cluster for high speed digital components. So coming to FPGAs, memory, and other controllers, these are the logical modules in the circuitry. So analog is the continuous signals, and power is the high voltage, high current rated domain. And coming to the digital, high speed, high transactions. So So zeros ones will be triggered very quickly. So we can say like these are high speed digital components, high speed digital signals. So we should maintain separate cluster for these components as well. And coming to again decoupling capacitors, we need to place as close as possible. And coming to the digital components, uh, coming to the digital components, we should keep all the components, similar kind components at the same place. The purpose is it will be useful for routing. If you are placing all the digital components in the single block or near similar block, so that it will be easy for the designer to go for a like easy tracks. That's the one thing. And the second one is debugging will be very easy. While we are keeping all the components, all the similar kind of components at single place, it will be easy for anyone to go for a easy layout, at the same time easy debugging. And as we already said, we should maintain this particular track length as close as possible to avoid crosstalk or else EMI effects. So EMF effects. That's it about this particular digital circuit components. So these are like there are three particular type of signals. One is power, and the second one is analog, and third one is digital. We should maintain all the blocks as a separate block. And coming to power, we should maintain as distance as possible to analog and digital, because these signals are very sensitive. If we are getting even a small noise, the signal will be corrupted. So that's the thing about this particular component placement. And coming to the routing, so there are we can say about single layer and multi-layer. Single layer, it's simply about the PCB will be having only one-sided single layer tracks. So for your kind understanding, let me explain. So there are no tracks on the other end. If you take this particular PCB, so if you take this particular PCB, there are tracks on top side and tracks on bottom side. This we can say as a multi-layer PCB. So most of the PCBs, these PCBs are bit higher cost when compared to the single-sided PCB. So coming to single-sided PCB, we doesn't require the other side tracking. So only one side tracks will be there. So coming to the cost, which is cheaper among all the layers. So single layer, very cheap when compared to the other thing. And this is very preferable when the components are less in count. If the components are great in count, the components is huge in count, then we should go for a multi-layer. Obviously, because we should not go for a PCB size increasing. If it is like there are components from back side, bottom side, and top side. So we can place these particular components like bottom components on the single side, so that the size of the PCB will be increased. But which is unwanted thing. Thing here is, if you're going for a single side PCB, the cost will be low, but the signal immunity will be destroyed, because we should maintain tracks as lower as possible. So if you are placing these components in the top side, so that the size of the PCB will be going high, and that we need to maintain the tracks, then track length will be increased. So which is undesired condition. So if the components are less, then we can go for a single side. If the components count is huge, then we should go for a double sided. We will discuss about how the connection will be happen from top layer to bottom layer in the coming slides. There is a concept called wires. So using wires, there will be a communication establishment between top layer to bottom layer. So coming to single layer, which is best possible thing. So for lower components and lower size, and here we need to plan carefully, because as it is a one-sided, there is no chance for overlapping of the tracks. This is the track. This track can't be overlapped with other track, because both are on the same layer. So we can't we should maintain careful. We should be very careful while tracks are planning. So there will be a chance for tracks overlapping. If the tracks are overlapping, then boom, everything will be damaged. So this is what one of the thing very essential. And if any external connection is required, we need to use for physical jumpers. Like let us assume there is a connection required from this point to this point. But if you are going for this particular connection, let us assume there is a track for this particular capacitors. So there will be no chance to run the track from this particular point to that particular point. So we should go for a physical connection, which is undesired, completely undesired. So if the compounds are whose intensity, then we should go for double side at the cost of increasing in financial, like increasing the BOM cost. So that's all about single layer. So I already told, right, when we are going for a long traces can introduce noise and delays. We can make higher density compounds also in a single layer, but the noise immunity will be lesser and the delay in the signal will be improved. So delay will takes place. So we need to maintain compounds as close as possible. Let me add one more point so that you can ask, like, so PCB, there are a number of compounds. Can we place all the compounds very close to each other? If you are making all the compounds very, very close, then there will be a signal cross talking. That's the first thing. And electromagnetic interference will take place. So we should maintain some separation between track to track. That is what track separation width. Okay. So I said, right, there should be a spacing, but you should not go beyond over spacing. If you are going for a over spacing, if you are going for a loop area improved, then EMF effect will be created. So this loop area should be minimal. If you are going for a completely reduction of this particular loop area, then crosstalk will take place. So we should maintain proper spacing between the components. So coming to single layer, we should not go for a long traces. If it is a whose density in the compounds, then we should go for a dual layer. Okay. So now we'll see about one hands-on circuitry with this particular a single layer PCB. Shall we? Just give me a second. Am I audible?
Yes, sir.
Yes, yes. Thank you. Thank you for update. Yes. Just give me a second. So let me off my camera. Yeah. So let me explain about single layer. So is my screen is visible? So these were the DC-DC buck converter.
Yes, yes.
Okay. So if you see, these are the power related tracks, and these are the signal related tracks. So you can simply observe the width of the tracks. So power basically recommends higher width. When we are going for a lower width, then there will be a damage in the tracks. So we should maintain proper track. If it is like a, let me explain with simple words. If the current will be like 1 ampere, we should maintain 2.5 times. The track width should be like 2.5 times of the nominal uses of the current flowing. Okay, and this is about signal tracks. So if you see, there are no other tracks in the back layer, like bottom layer. So let me showcase with the bottom layer. So these were the PCB buck converter. Okay, so we will apply input at J1 and output we will get at J2. So all the tracks, if you see, like all the tracks on the top layer only. These are the some of the tracks. Okay, so we'll see in the bottom layer, there are no tracks you can observe. These were the single layer PCB. So no tracks you can observe. So if you go for a top layer, there are very few components. Okay, so no track can't be overlapped with any track. So that compounds will be like crosstalk will take place and short circuit will take place. And the compounds are also lower in count. And if you see, this is the power track which is having a higher width, and these are the signal related components. So that is about single layer PCB. Now we'll get back with our presentation again. So again, let me get back for our presentation. So that is about single layer. So physically, if any connection is required, we should go for physical jumper connection. So this is what physical jumper connection, which is unwanted thing. So now we will see about dual layer. This is very interesting topic. So coming to multi-layer, so single layer, it's a simple thing. There are power tracks, signal tracks. We will run the signal tracks first. Okay, we will run the signal tracks first. Later we will go for a power tracks. Power tracks are higher in width and signal tracks are lower in width. All the components length should be as close as possible. So that is about simply about single layer. Coming to the multi-layer, multi-layer here, if you say there are, like, you can count like layer 1, layer 2, layer 3. For your understanding, we are simply like there are in the PCB there are multiple layers, like sandwich, like layer by layer. Okay, this is what the top layer, this is what the layer 2 inner layers, and this is what outer layers. So thing here is there are some technical terms we should go for a multi-layer routing. The first one is use differential pair routing. For higher speed signals like USB, HDMI, and Ethernet, we should go for a. So let me showcase, like after this particular 4 points discussion, we will go for a what is exactly differential pair, what exactly wires. We will see everything in detail. So differential pair is nothing but let me take a RS485 communication lines. There is a line, B line, and coming to 232, A plus, A minus. These kind of signals we need to pair together because these are high speed signals, and we should maintain parallel tracks, and there should be a uniformity. If there are any two differential pair of signals, there should be a uniformity. And in terms of speed, if A minus A plus is there, okay, A plus A minus is there, while we are sending signal, that signal should be traveled from for both A plus and A minus. If the both the tracks are far away to each other, there may be a chance for noise. So both the tracks are as close as possible, and both the tracks are parallel to each other. So that is what the concept of digital pair. So we will differential pair we will discuss in detail using this particular example. And second thing is wires. Wires is nothing but connecting factors. Like wires will be used to connect from one layer to other layer. If we take a single layer, all the components, all the layers, all the tracks will be on the only one side. If you go for a back side, so see, let me on my camera. Just give me a second. So these are. Can you off the blur? Do you know, like, can just
Correct.
thank you. So if you take this particular PCB, this is the bottom layer, and this is what the top layer. Okay, so this is what one of the PCBs. So how can we? This is the controller, simple controller. So there are tracks in the back layer. So these are the connectors. Okay, so to make this particular connection on the top layer, like on the top layer also there are few components. If you see, there are few components. So wires is there, like it is impossible, I guess. So there are for our simple understanding, there is a holes kind of thing, holes, like it's very difficult, I guess. So holes are there. So this particular, just give me a second. So it's difficult. Chalo, fine, no worries. So from this particular layer, there will be a wires. That wires, we are taking the connection. That connection will be make use here, so that we can use same space on the PCBs. Can use same space on the PCBs. So that is about the wires concept. So I will explain everything with the software as well. So coming to the inner layers and dedicated power layers and planes. So on top layer, mostly on top layer, we are assigning for signals. That might be digital signals or else analog signals. The top layer will be utilized for signals. That might be analog signal or digital signal. In the inner layers, those will be allocated for power and ground. We should maintain separate plane, separate layer, separate plane for power. For both power and ground planes, we should maintain dedicated planes, so that uniformity will, continuous stack will be there, so that heat dissipation will be reduced and the signal integrity will be improved. So that's why we are maintaining dedicated layer for both power and ground planes. and the top layer will be meant for signals. So the connection will be happening through wires. So let me explain about, like, coming to the last one, follow impedance matching techniques. Thing here is, high frequency signals are there, like digital signals are high frequency signals. The transaction is very, very fast. Okay. So while we are dealing with the digital signals, we should take care about prevention of signal loss, so that we should try to maintain signal impedance, so that length is as close as possible. The track length is as close as possible, as shorter as possible, to maintain the impedance. So we will go for a demo. So just give me a second. So let me explain about differential pair. So this is one of our PCB, that is hybrid water purifier unit, which is we designed for one of our clients. So here there are two lines. Just give me a second. So for differential pair, I already said, like, for Ethernet and USB, we should maintain about that particular thing. So first we should select two differential lines, either A plus or A minus. We should select two lines, differential pair selection. So once differential pair DP1, DP2, these are the differential pair. So positive net PC1 and negative net PC3. So we are going to apply differential pair for this particular thing. So these are PC1 and PC3. So if you see, both the tracks are starting from same point, and both are going in a parallel way. Simultaneously, both are, like, we need to we no need to draw like PC1, PC3 separately. At a time, we can draw both the things, and you can observe one more thing: both are very parallel. Both are parallel. So that is what the concept of this particular differential pair. Okay. So let me come back to the presentation, and now we will see about PCB design constraints. So there are electrical connections. We already discussed. Like PCB design constraints. The trace width and space should be maintained. The trace length as short as possible. So if you are going for a increasing the trace length, then it is unwanted thing, because noise will be introduced and the signal will be weak. So the trace length should be as shorter as possible. At the same time, we should maintain width and spacing accordingly based on the signal. So if it is like a power, we should maintain high width. If it is like a signal, lower width is sufficient. And spacing, power and space, and we should maintain space as per requirement. If the space is very, very low, then the heat dissipation is very high. Then signal noise will be generated and signal will be lost. So we should take care about heat generation, like we should take care about heat dissipation. Okay. And controlled impedance matching for high speed signals we already discussed, and minimal loop area in high frequency circuits to reduce EMI. So we already discussed, like, EMI is the one thing which will interfere with other signal, and which will destroy the other signal. So we should maintain loop area as close as possible in the high frequency circuits. So coming to the mechanical constraints, the board is as small as possible for both enclosure aspect and form factor aspect. If you go for if you go for a larger size in the PCB, with unwanted cases, like if the components are too high, then we can go for a two layer and multiple layers. If the components are very low and we go for a dual layer, which is unwanted thing, cost should be increased. If the components are too high, still if you want to go for a single layer, then the length of the PCB will be increased. So the board size will ultimately be increased. So which is undesired thing. And one more thing, keep the components within assembly clearances. So if you are going for a mechanical housing, all the components should be placed inside the particular casing, and hole sizes, like through hole components, should be matched for the holes. Like already we provide that particular hole provision for through hole components, both should be mapped. If we able to mismatch the footprint, so at the time of PCB arrival, the components won't be fit. So if we take our PCB, so there is a issue in footprint. Just let me explain. So we hand over this particular PCB to some of the junior engineer in our office. Okay. So he planned, like, so pin to pin, there is a, like, we can call it as a thing is, there is a spacing between this particular header to this particular header. So this is called footprint. So this particular designer is mismatch this in this particular footprint. So they keep these particular tracks far away. So while we are trying to fit this particular thing, it's unable to fit. We need to work on this particular thing. This is what the importance of this particular footprint. So while designing, we should take care about footprint. So that is what the importance of through hole. So all the components footprint should be matched so that whenever we will purchase the components, it will be matched with the particular footprint. So coming to the PCB design constraints and rules, we already discussed sufficient space should be there, or else between tracks or else pads. So if there is no spacing, heat will be produced. Eventually, noise will be generated, signal will be destroyed, and we should maintain minimum number of wires to reduce the cost and complexity. If the number of wires, if we can go for a like if the and there are huge components, we should there is a space constant on the PCB. We are planning for to reduce the PCB size. We are going for a multi-layer with multiple through holes, multiple wires. Are you getting? Are you following? There are there is a size in the PCB, okay, but compounds are whose density. So we are planning for multi-layer PCB. At that case, the number of wires will be increased, which is undesired case. If the compounds are huge, we should go for a better higher size of the PCB, so that the number of wires will be reduced. Eventually, the cost of the PCB will be come down. Okay, and we need to use soldering mask, the green color one, which you already seen. The green color one, the green color one we called as a solder mask. We should keep that solder mask to prevent from soldering, like shorting of the components. So we should once etching is done, we should go for a solder masking. So that is about PCB rules. So this simply like thermal constraints. So all the components simply generates the heat. So mostly power circuits will generate the thermal. So we need to go for a thermal wires under high heat generation component so that there will be air circulation. The heat will be come down. There should be a wires, thermal wires for the power components. And one more thing, copper pour should be higher. We should pour as much as copper for high power circuits to improve the higher heat dissipation. So this copper pour will greatly support to reduce the uh, heat on the circuitry on the PCB. So now we will discuss about power and ground plane design for stability. So thing is very simple. If you take any PCB, first we will go for a components placement. Thereafter we will go for a power planes. Power we should go for a separate dedicated planes so that there will be a continuity and uniform distribution. So even voltage distribution, there will be a chance for even voltage distribution. If you go for a dedicated plane for power, there will be a chance for even voltage distribution, so that there will be a minimal voltage drops. And again, we need to place decoupling capacitors as close as possible for all the power rated circuits to reduce the noise. So now we will see some of our hands-on routing for coming 5 to 10 minutes. Thereafter, we will go for a most probably a explanation will be covered tomorrow. So now we will see about real-time routing for a multi-layer PCB in easy EDA. So I guess like Mr. Sai Shankar will cover the hands-on routing. So just now I came to know. So we will go for a theory.
Sudhir, yesterday related to the
So now
schematic.
we will discuss about.
Sorry to interrupt, Sudhir.
Yeah, no worries.
Yesterday we have covered the schematic drafting and routing layout along with the 3D view also how it looks like. You can skip on that front and you can cover the AI related info. If any one of the faculty is having doubts after the session, we can discuss on that front also.
Yes, Sai Shankar joined. He's ready to doubts clarify. So we will go for AI related, so that we will open for doubts clarification. So simple thing, there is a DRC checklist. So without DRC checklist proven, we can't move forward. Now, AI tools are integrated to check the DRC checklist. That is the first thing. Every designer, this particular AI integration will be helpful to improve DRC checklist. Like errors, it's pointing to where the exactly errors and how can we resolve those particular errors. This is what the inclusion of this particular AI in the DRC checklist errors projection, error resolve, and techniques. And it will the AI tools will recommend what is the track space we need to maintain based on our requirement, based on the component specifications. And it will explain like size of the wire based on the current flowing through the particular track. If you are going for a small diameter wire, then it will recommend we can improve the size of the wire. So these kind of suggestions we are getting in the AI integrations. And one more thing, in before AI, we need to go for a vendor location. We need to check whether the component is available or not, whether the footprint is matched or not. Now the AI tools will reduce our manual work power. So before sending to the manufacturer, we will check all the components availability using AI tools, so that if the component is not available at the store, we can go for a similar kind of footprint component replacement. That's the one thing. Second thing, if any footprint and any component mismatch, that AI tool will recommend us this footprint and the component is mismatched, so that before going for a manufacturing, before getting this kind of PCBs, we have a chance to correct it in the software itself. So the AI will help us to placement strategy routing. So it will be helpful for BOM tools, like BOM is available or not at vendor, and it will be helpful for DFM, and it will be useful for design rules checklist. So this is how AI tools will be helpful. So AI will also analyze the power distribution network. While if you are going for if you are giving a requirement in the design tool itself, it is recommending us what should be the track width, what should be the track length, and what is the direction of that particular track. So if you are going for a track width, if you are minimizing the track width, so it won't allow us to go further. So we should obviously go with AI recommendations. So if there are any analog and digital and power segmentation, it's recommending us. So you should maintain both the things simultaneously. Like there should be a separation between analog and digital. So these are the decoupling capacitor placement. If you are keeping decoupling capacitors far away, it's recommending us to keep the decoupling capacitor towards the particular power module. So these are some of the AI recommendations, AI powered PDN design explanations. At the same time, AI interpretation of signal integrity requirements. So it will be help us for impedance control, the track width, spacing and setup, and crosstalk from parallel routing. We already discussed about parallel tracks, so it will be helpful for that particular thing. Differential pair, length matching, and wire suggestions. So everything is happening with AI in nowadays. So simplifying layout constraints into the engineering logic. So before AI, we need to go for every CRC checklist manually. We need to go for each and everything manually. We need to check each and everything manually. Now these particular tools are AI enabled, so that it will recommend whether that particular track width is acceptable or not. Do we need to increase the track width, and do we need to reduce the track length? All the recommendations are given in the info table itself. So that is how the AI integration in nowadays. So that's all for today. So me and Sai Shankar are open for doubts clarification. So let me hand over session to Mr. Sai Shankar for doubts clarification. Yeah, please.
How much should be spacing between the components? Okay. I said how to calculate trace. Yeah, coming to the session, coming to the doubts
Sir, I
session,
have
you can
one
drop your
doubt.
any doubt in the
The
chat box
multi-layer
and I'll look into the.
PCB,
Yes, sir, please.
is any possibility to occurring the frequency interval?
Sir, I think there is a bandwidth issue or internet connectivity issue from your side. I can't able to understand fully
Hello?
what you're asking. Yes,
Hello?
sir. Yes, sir. Ah, yes, sir.
Sir, I check.
Sir,
Hello?
can you enter the question in chat box because the internet connectivity from your side, I think it was too bad. Okay, Mr. Naga sir, you can drop the question in chat box, sir. That will be helpful. I will explain that in detail. Something I heard like antenna related something you are asking. Okay. Suma ma'am is asking some doubt like how much should be the spacing between the components, where there will be multiple variables with respect to the spacing of a component, ma'am. When we are dealing with a power supply related circuitries, usually they will produce lot of heat. So there will be an recommendations from the data sheet itself to keep minimum spacing to avoid the heat constraints, as well as when we are dealing with an SMD component and through hole components, we will always keep that in our mind based on the fabricator feasibility to produce the PCB. Because when we are doing the manual soldering or doing an assembly level soldering, the technique of soldering will be plays crucial role over here to place the components as near as far as possible. That is one thing. And uh, hi sir, how to calculate the trace width? Usually, as we have discussed previous sessions also, the trace width will be calculated based on the current requirement of the PCB. When ideally the 35 microns PCB with 1 ml, the standard thumb rule is like of a copper PCB, 1 mil carries 10 milliamps of a current. Okay, based on that current calculation and current requirement, we will be doing our current track widths. Let us say if we want to design an or connect two points which need to carry in 160 ohms, sorry, 160 milliamps of current, we will be giving in 16 mils of tracks over there. That is how we will usually do. So as a thumb rule in the industry, we will follow like 1 mil is equal to 10 milliamps for 35 microns. If you want to increase within the same range, you can increase the track height size like from 35 microns to 70 microns. So 75 microns of single 1 mil track will carry 20 milliamps of current. Based on that, we will be doing accordingly. In multi-layer PCB, is there any frequency interference? Yes, sir. In some case, when we are dealing with in very high frequency signals, then usually we will have such kind of interference. But a lot of radio related things will usually act in gigahertz or in megahertz when we are ideally doing, or if those when all the signals in the PCB might be in megahertz but not in more than gigahertz. That is the reason lot of signals will be null and avoided. Along with when we are doing with high frequency signals, ideally we will provide the ground shielding also. So because of the ground shielding, the it will creates like an Faraday's case. Because of that phenomena, it will arrest all the RF signals and it will kill RF interference on the signals and it will be avoided, sir. According to customer requirements, how to design PCB? He has a sequence of flow as we have discussed it from the very beginning. Based on the requirements gathered, we have to do our analysis and we have to finalize our blocks how wanted to do. And after finalizing your blocks, we have to thoroughly do our testings. And if we have very clarity on what we are doing, we can jump into the schematic design also. We will Before jumping into the schematic design, we will be checking availability of every components, everything as how we have discussed. And after that, we will be finalizing the schematic. We will be doing the simulations if we wanted to, or otherwise we will do the routing and we will finalize the PCB. And post that, we will be sending it to the fabricator. We will be getting the actual PCBs. We will do the soldering. And in the coming day session, we will be seeing what is the after process of the PCB and how real PCBs will also be done, the manufacturing process, and how to send the Gerber files to the fabricator. All of these details will be going into the next session. By that, you will be having full clarity on how you will get in physical PCB in your hands. Post that, you will be developing your source code and you will be dumping the code into the modules and you can use it in the real-time environments. In the further going session or the second of this FDP session, we will be covering this coding related information also. So by that, you can have clarity on PCB front as well as firmware front, kind of a complete embedded life cycle. I think that answers your question, Mr. Srihari. Does anyone have tried regarding designing any small PCB or the same circuitry in easy EDA by any chance? Anyone faced any hookups or any difficulties while doing that? Please try to do that design once with your hands-on experience. So listening a class will might give you an 30 to 50% of knowledge for you, but you doing it manually from your end, you will be facing a lot of hookups and difficulties. Then you will ask yourself, why are you choosing that particular option and what is the use of other options? By exploring that by yourself, you will get lot of more knowledge than the discussing things. So that is my suggestion or my recommendation from my side. If you guys still have any doubts, we can continue on that front, or otherwise I think you can leave from the room. Mr. Surya, you can take up from here.
Surya is occupied with other meeting, so thank you, respected faculty members. So I request everyone to please continue for next week as well. So by tomorrow we are going to close this particular PCB related thing, and from Monday onwards we are going for a firmware. So request everyone to be actively part of this particular thing, and we are open for collaborations for both skill links. So we are having CSR fund at this at our company. So we just want to do something with CSR fund, and we are open for collaborations for skilling and hiring and Center of Excellence collaboration and R&D support. So thank you everyone for joining in the meet.